Okay, so welcome everyone to the Bangalore Probability Seminar. This is the first meeting for this semester, and we have two talks as usual related. So it is a great pleasure for me to introduce Alon Nishry from Tel-Aviv University. So I first met him 12 years ago when he was a master's student. Since then, it looks like his displacement is very little. He has moved to a faculty office from the grad student office. So, but in between, he has produced some of the most non-trivial and deepest results in this subject of zeros of random analytic functions. So it's a real pleasure to have him here. Today, he is going to talk about Gaussian complex zeros, conditional distributions of rare events.
Yes, thank you very much for the great introduction. My pleasure to give the talk. I'm very happy for this opportunity. I was supposed to be in a conference last month in India, but you know how it ended. So I'm great that I have at least this opportunity to give this talk. So I will talk about, in general, give some background about this question of the conditional distribution of point processes on rare events, and in particular about what I call for short Gaussian complex zeros, which I will explain. And this is based on a work from several years ago with Subro Ghosh from National University of Singapore, and a recent work with Aron, also from Tel Aviv, and he will provide also more details in the next talk. So this talk will be with very little technical details, just to sort of give the setting and the feeling of what kind of problems we are dealing with. So I will start with a sort of a description of what we are doing, but for a model which is kind of not very exciting for the type of questions that we are going to ask, but it's sort of just to give the feeling of what type of question we are asking. So we can think of the homogeneous Poisson point process. I will just talk about processes in the plane. So we can think of this process in equilibrium, so without any conditioning. And then we sort of look at a certain disk. We think of it as a large disk that contains many points, and we want to condition on this on the process on the event that there are a few, let's say, few points in this large disk compared to the expected value. So for the Poisson process, we know exactly what will happen. This is just thinning. We will at random can pick the probability that each point will sort of disappear, and each of the points can do it independently, and nothing will happen to the points outside. So in the sense, for the Poisson point process, it's like a gas of particles that have no interactions between them. So if we want to condition on some event, which is kind of rare, that we have very few zeros in a disk, still we won't, except of course in the disk itself where we condition on a rare event, the process outside will not see at all what is going on inside this disk, and we won't see any effect. And now the question is whether there are processes for which this question has a more interesting answer in terms of what is the probability of the event that the number of zeros in a large domain is very far from the expected value, and also if we condition on such a rare event, how the process will look like after conditioning. So I will talk very quickly about the kind of processes that are interesting. I'll just talk about two examples. The Geneva Ensemble, which we can think of as random eigenvalues, and the zeros of the Gaussian Entire Functions, Gaussian Entire Function. Then I will describe the specific rare events that we are interested in, and sort of the framework to deal with these questions. And finally, I will talk a bit about the relation between a potential theory and this limiting distributions that are conditioned on these rare events. And Aron will give more technical details about the third step in his talk. Okay, so let me quickly talk about invariant point processes. Again, I already consider the plane. Maybe at one point I will mention results on the real line. And by the way, of course, you're free to ask me questions either in the chat or live as you wish. So we have a point process, a random collection of points, or a random discrete measure in the plane with no accumulation point. We denote for a nice set G, we denote by n of G or n subscript x of G. The number of points is the random variable that counts the number of points of the process inside G. And the assumption is that the distribution of the process is invariant with respect to isometries of the plane, so rotations and translations and reflections. So these processes are kind of have like a real, in some sense, some physical meaning or something vague like this. In a sense, they are the most interesting processes to study because questions of, for example, of the types that we are asking about statistical properties of this random variable have answers in terms of the geometry of the set G, the location and the way we rotate the shape is not important. And of course, the most well-known and well-studied case is a homogeneous point process, a Poisson point process, where this random variable is just a Poisson random variable. But for us, it will be more interesting to study these two processes, the infinite Ginibre ensemble that I'm going to describe shortly, and the zeros of the Gaussian entire function. And both of these processes are very different in a sense from the Poisson point process, because there is some interaction, non-trivial interaction between the points or the particles, and they are kind of similar to, these two are much more similar to each other compared to the Poisson point process, but still there are differences between them, and part of what we are interested in is sort of studying these differences. So I'm not going to talk too much about the details of the Ginibre ensemble, but we can think of it as simply there is a finite ensemble that we just take an n by n matrix. We put at each entry independent, a complex Gaussian random variable. All of them are independent with no symmetry. We end up, of course, because there is the matrix is not Hermitian. We have complex eigenvalues, and this is a determinantal point process. So I'm not going to go into the details of what this means, but roughly speaking, it means that if you want to do computations about the distribution of the points, this can be done in terms of some integral operator with some given kernel. At least in principle, computations can be done in terms of this kernel. And then if we take the size of the matrix to infinity, we can define a convergence of point processes to a limiting point process, which is an infinite Ginibre ensemble. It's also a determinantal point process. And we can think of it as a sort of a gas with interactions between the particles. The interaction is repulsion, so we can think of this gas of being a gas of electrons, which is kind of embedded in a uniform background of a positive charge, and the particles just have a repulsion between each of them. Okay, so this is a Geneva ensemble, studied by many since it was introduced by Ginibre sometime in the 60s. The other model, which is like the star of the talk, is a Gaussian entire function, and more precisely the zeros. So we again work with independent complex Gaussians. We form an entire function by writing down a Taylor series with random coefficients psi n times d to the n over square root of n factorial. And if we choose this normalization for the Taylor coefficients, it's easy to check that f is actually has an infinite radius of convergence. So it is an entire function almost surely. So we may look at its zero set. Because it is an entire function, this is a discrete set of points in the complex plane, so we may think of it as a point process. It turns out that the multiplicity of the zeros, so there is no multiplicity, the zeros are simple almost surely, so it's a simple point process. And then we can ask about its properties. It is unfortunately not a determinantal point process, so computations, even the basic ones are in general more difficult. And also there is really a more complicated interaction between the particles or the zeros. It's no longer a point-to-point interaction. There is some point-to-point interaction, and there is some multi-point-to-point interaction, which is more complicated. However, on short scales, the behavior is similar to the Geneva Ensemble. There is a repulsion between the zeros. So there are many similarities between these two processes. So I'll show it in this following some pictures. This is the Poisson point process. So we see there are many clumps, and there are sort of regions where there are no points. While for the Geneva Ensemble, because of the repulsion, the behavior is much more regular. And for the zeros, they basically look the same. First look, at least, they look almost exactly the same. And now the question is, which properties distinguish between these two processes? So here, this is what I call how the processes look like in equilibrium, where we don't do any conditioning, just a sort of sample randomly from the process. And of course, I normalize all of them to have the same intensity or the same per unit area, there is the same expected number of points. So now we go to rare events where this process will start to look not exactly the same, but we will start to see some differences. So it is convenient, instead of what we want to ask is questions about large domains. So instead of that, it is sometimes technically simpler to fix the domain and study processes with higher and higher intensity. So this is what we do. We rescale the process so that the intensity grows like R squared. We normalize it in some way so that the number of zeros in the disk, in the unit disk, is just 1. And then we scale it to grow like R squared, and we want to study the process as R goes to infinity. And so for the Geneva Ensemble, because of this determinantal structure, it's very, very well understood as a statistical behavior, at least in principle, of this point counting function. For the zeros of the Gaussian entire function, it's also now reasonably well understood, I would say. So starting there were results about the variance, starting with a work of Forrester and Horner, and then there were many results by Sodin and Theoson in all kinds of directions about central limit theorem and the variance, and also about large and model deviations. So Manju contributed to the understanding of overcrowding of the zero process. And there are also results about all kinds of different large and moderate deviations that maybe I will mention later. And we are interested in rare events. So the most typical one, and also the one which we understand the best, is the Hall event, where we just condition on the event that there are just no points in a large domain. Because this is a large domain, this is the probability of this event is extremely small. But we may also ask what happens where we have just a deficiency. So instead of having the expected number of points, which is like r squared, let's say if we have if this is the unit disk, then it will be r squared. We ask what's the probability that we have half of the number of points, and because the variance is of order r, the fluctuations are of order square root of r, the typical fluctuations, and this event is well outside the central limit theorem, so it's extremely small probability, and we would like to see how it affects the process if we have such an event occur. And the other possibility is also to study, of course, overcrowding, where the number of zeros is much bigger than the expected number. So these are the typical events that we would like to consider. And here we already see differences between the processes. So I will show in the picture in a bit. So just to be a bit more concrete, let's ask what happens, let's say, on the whole event. So as we take the intensity of the rescale process to infinity, what will be the asymptotic rate of decay of this event that there are no zeros in the set G, and how this depends on the geometry of the set G is not a trivial question. And this is the limiting. What will be the limiting spatial distribution of the points if we condition on this rare event? So, so informally, how the process will look like if we just say that we condition on this rare event that there are no points, how the process will look like. So for Poisson processes already described, this is not an exciting question. It follows immediately from the definition what is the probability of these events. And also the conditioning is trivial because of the independence property of Poisson. Just outside the domain G, we are not going to see at all the effect of this event. But for Ginibre, this is already an interesting question. We can use the determinantal structure, and we can also use the potential theory to answer this question. I will try to explain what I mean by that. But the principle is a sort of, in order to do this, we need to have a way to approximate our process with processes that have finitely many points, because those are the ones which are accessible for most questions. For some questions, we can directly handle the infinite Geneva ensemble. And this approximation is not entirely trivial because we are dealing with events which have extremely small probabilities, so we need a very precise approximation. But I will not get into the details of how this is obtained too much. This is not completely resolved even for the Geneva ensemble. But pictures I can always show. So here we can consider two examples. So here there is a deficiency. I think this is 1/4 of the expected number of zeros in the unit disk for large intensity. So we see the Ginibre ensemble behaves somewhat as we expect a gas of particles, that there is some interaction and the number of points is conserved. We cannot just erase points like we did for the Poisson point process. So the points basically go to the boundary. If we want to have fewer points inside the unit disk, we take the extra points to the boundary. And what happens is the rest of the gas outside is not completely oblivious to what's going on inside. The points just stay on the boundary and nothing happens. Exciting happens outside, well away from the disk. Overcrowding is similar, but instead we bring more points from the outside. We just put them on the boundary of the disk, and inside the disk nothing interesting is happening, and also far away we don't see anything. So this is what we get for the Geneva Ensemble. So this is part of the result with Subro is what happens for the zeros, and this is already very unexpected. First of all, the pictures look almost the same. I will not talk too much about it, but we found some type of duality between deficiency and overcrowding. For deficiency, it turns out that for the zeros, actually, so here the unit disk is just inside. So we have, of course, to remove some zeros from the unit disk and move them to the boundary, but the very, very surprising phenomena is that you also have to take some zeros from the outside to balance and bring them to the boundary. So you have to find some balance between the inside and the outside in order to obtain this deficiency that you have less points than expected. And for the overcrowding, it's the same. If you want to have more zeros inside the unit disk, then actually you don't just bring points from the outside. Now this circle, so-called, is just many zeros which are located just inside the unit disk. So you bring zeros from the outside, but actually you have to remove some zeros from the inside for balancing. Of course, here in this situation, at some point, if the overcrowding is too big, then we will exhaust all the zeros that are inside, and we'll just at some point move them to the boundary, and then we just keep bringing more zeros from the outside. But this balancing is very surprising. That the picture basically looks almost the same, despite these events being completely different.
Just a question, Alon. In this deficiency and overcrowding, can you say the conditioning is on the smaller disk, right? I mean, on the disk, where's the conditioned event?
Conditioning is on this disk. Let's try to draw it with a color. So the conditioning is on the, I don't know if you can see the blue one.
Yes, we can.
So the black circle, so-called black circle, is actually the zeros themselves that accumulate near the boundary of the disk. When overcrowding, they accumulate just inside, and where there is a deficiency, they accumulate outside.
Okay.
So let me explain how do we approach such a problem using large deviations for the empirical distribution of the points of a process. So the assumption here is that there is some way to approximate the rescaled process by a process with finitely many points, which I denote by xn. And then we can write a probability measure for this process that have just finitely many points. We just put a delta mass at each of the points and weight it to be a probability measure. And then informally, a large deviation principle for the sequence of empirical measure roughly means the following. If I take a nice subset of the probability measures on the complex plane, then the probability, if I take empirical measure distributed according to this process with endpoints, and ask what's the probability that this empirical measure falls inside this nice set, then after taking logarithm, this probability can be given by some constant going to infinity, which I denote by n, time as the infimum of some functional acting on probability measures, where I take the infimum over this set C. So what we can think of it is informally is that this set C of probability measures give us the sort of we have some configurations C inside the set of probability measures, all of probability measures, and then we are looking for this configuration which is optimal in the sense that the probability of this configuration is the largest. And if we have this large deviation principle, and if this set C is nice, then the point which maximizes the probability, in a sense, it is the one that will determine the probability of the rare event. And the question is, of course, how to find this extremal value of the functional. The reason we take an infimum is because this is usual to write it with a negative sign. So we want to maximize the probability. So we have to take the infimum over the functional. And this functional is called usually the rate function. And for the Ginibre ensemble, this was done by Ya and Petz and Benarus and Zeytouni at the end of the 90s. They both works did a bit. This one was a bit more general, and this was a bit different process, but essentially it holds in the same way for the Ginibre ensemble, for the finite Ginibre ensemble, which again I remind is just eigenvalues of n by n matrices with IID complex Gaussian entries. Here we have a very nice expression for the joint density with the right normalization. So if we denote the eigenvalues by W1 to Wn, which are again complex numbers, then the joint density is a product of a van der Monde term. So this is a particle-to-particle interaction because it depends on the distance between the points. And we have some external factor, which if we had just these factors, then all the particles, in a sense, would run away to infinity, and this keeps them at place. And very roughly speaking, the probability of rare event is sort of is determined by trying to maximize this expression. And if we have a sort of allowed configurations, for example, that we want all the W's to be outside of some domain, then we just try to find the maximum of this expression over all allowed locations of the W's, and this will give the probability of the rare event. This is very roughly speaking, of course. So to explain how do we find this rate function in the case of the Geneva ensemble, so this requires some computation. Because we work in the logarithmic scale for large deviations, we can rewrite the expression in the following way. So now we see really this point-to-point logarithmic interaction between each pair of points. And we have this added term, which called the external field. So the second term, we may rewrite in terms of integration against the empirical measure of the points, the integration of mod W squared, which we call external field. It's the one that keeps from the point from running to infinity. And if we ignore technical problems, that's a singularity on the diagonal, we can write the point-to-point interaction as a double integral of the logarithm of 1 over the distance between the points with respect to the empirical measure. And this thing is called the energy or logarithmic energy of the measure. So if we combine these two terms together and we add up the normalization constant, then we get that the rate function is the integral mod W squared with respect to the measure plus the logarithmic energy, okay, plus some constant, normalization constant. And this is exactly the function as it determines the probability of a configuration. So for example, let's the easiest example is the whole event. So we want to consider events where we have no points inside the given domain. So no points inside the given domain means that the empirical measure doesn't charge this domain. So in the limit, we are interested in measures that give zero mass to this domain. So this is the set of measures on which we want to study the rate function. So I say as a remark, actually the classical large deviation theory doesn't work with such subsets of probability measure because it's not good in a sense that it has an empty interior. So it's topologically not good, but still you can do it. It's just technically more demanding. And you have to choose this approximation parameter. So we are dealing with a process with the intensity scaling like R squared. So typically they are about the number of points in this domain will be proportional R to R squared, and then let's say that we take this truncation parameter n to be proportional to this R squared. In reality, this is more complicated. Maybe Aron will talk a bit about it in his talk. And then, roughly speaking, the probability of this event, that we have no zeros for the original process, is comparable up to some error terms to the probability that the finite process has the empirical measure in the set of interest for us, so that there are no zeros in this domain. And this we already can deduce by large deviations. Well, not exactly, but approximately. And this is approximately minus n squared times the infimum of the rate function over this set of possible measures. And because n is like r squared, we get that this event decays like r to the fourth. So one thing that we get as a conclusion is that the whole event decays like e to the minus some constant r to the fourth. And this you can compare, for example, with Poisson, which decays like e to the minus constant times r squared, which is much, much slower. And the same rate holds also for the zeros. And this rate function is sometimes called weighted logarithmic energy, and it is well studied in potential theory. Yeah, the question that was asked, this normalization concept is just that if we don't do any conditioning, the minimizing measure is just a uniform measure in the appropriate disk where this approximating process exists, and this constant is just the constant that will make this rate function zero at the global minimum. Okay, so for the zero.
Alon, one question on this whole event. So it's possible that the empirical measure could charge it to be zero, but there could be a point, right, in the limit, because you are sort of taking the empirical this thing. Maybe it gives a very small fraction of points lie in the disk or so.
You mean here there will be some?
Yeah. If you take the finite measure, when you take the average over 1 over n, maybe in the limit it is possible that the point process actually, when you take n goes to infinity, the point process might have a point in the disk, but not the empirical measure. The limiting.
Yeah, what I'm saying, so this is very roughly speaking, what I'm saying that if we look for this, these are the admissible events, so we can relate so we can translate the probability that the original process has zero mass. This is the same as saying that the empirical measure, if the approximation is good. So here there is the fine point of what is a good approximation. So here there are some details. It's not a trivial thing, because when you do the approximation, you also might change the process a bit. Okay, so your question is important, but there are many technical details hiding behind this approximately the same.
Okay, thanks.
Mostly we can think about, heuristically, we can think about that this problem is just translated as is to a problem about a finite process. For the zeros, it's a bit more complicated to work with because of the non-trivial additional interaction on top of the point-to-point interaction. The basic approach is simple. We just scale the Taylor series, so we put an R here so that the whole process is scaled so that the number of zeros in a fixed disk grows like R squared. And then we approximate in the most natural way. We just truncate it. Instead of taking an infinite sum, we take a finite sum and get a polynomial. But the non-trivial part is like how to choose this n and how to show that the zeros. It's clear that the zeros of this thing will converge to the zeros of this, but we need a very precise estimate on this convergence, and this is not completely trivial. And then we can rewrite this polynomial as some terms, time harmonic polynomial Qn. it turns out that there is an expression for the joint density of the zeros, but it is more complicated. I will skip the details here, and Aron will provide more details. What I will say is that Zeytouni Zelgit found maybe 10 or a little bit more years ago that there is a large deviation for empirical measure of zeros of a Gaussian polynomial in a more general setting. And the rate function is more complicated. There is the same logarithmic energy term that there was before for the Ginibre, but now there is a sort of expression which is complicated. Before we just had a sort of term which was linear in terms of the measure, just an integral, and now it's a non-linear term which is also non-smooth in a sense because we have here a supremum. So this is more complicated to study. And sort of, it's not, as far as we know, it's a sort of a combination of things which were studied, but we never found a place where someone studied this specific functional, except, of course, this original work of Zeytouni and Zelgit, but there is no background work on from potential theories that we are aware of, so we had to develop some of it. So now the last thing that we want to say a bit is how do we study this limiting distribution. So again, the details will be in Aron's talk. But the interesting thing is that we have a heuristic principle that is sometimes called the Gibbs conditioning principle, which says the following: if we look at this set of probability measures we satisfy, let's say for the whole event, the admissible configurations are the ones that do not charge the whole, so the mass of the whole is 0. The scaling, yeah, the scaling is still out of the force. This is the same. And what the principle says is that the minimizing of this functional or the rate function corresponds to the limiting distribution of the processes on this event. So if we can find the measure out of this set of sort of admissible measures that minimizes the rate function, then we can also describe how the process looks like conditioned on this event. And then the question is how to solve this constraint minimization problem for functionals which turn out to be convex, so the problem has a unique solution, and how do we find the minimization problem? So let me go quickly over some results for the Geneva Ensemble. Here, the determinantal structure allows you some direct computations. First, there was a result in the physics literature by Yankovici, Lebovich, and Magnificat, and they gave a much more general prediction for processes which are finite processes, but more general than Geneva Ensemble. And they gave a prediction for the probability of these events, and they gave a prediction for how the process would look like conditioned on this event, and they gave even more general predictions for smaller deviations and for larger deviations, which I will call JLM predictions. Shirai proved some of the results for the infinite Geneva Ensemble, and also Adiakar and Reddy proved that the result for non-circular domains. So here it's mainly for the disk, and they proved the rate of decay of the whole probability for general domains. And there are also some works about the description of more general deficiency in overcrowding events.
Sorry, Alon.
Maybe I will skip. Yes.
In the previous slide, it's Scott Armstrong, right?
So sorry. Thanks. Good catch. Yes, Scott Armstrong first. I will skip the results in one dimension since we don't have much time, but there has been all kinds of work about one dimension. Maybe I would just mention that the original result in all of this direction was empirical large deviation principle that was proved by Ben-Arous and Guillaumet for the zeros of the GUE. And so several years ago with Subro, we studied the circular case. Here we don't have a determinantal structure, but we do use the radial symmetry. And what we get is that there is this thing that I already showed you, that there is this forbidden region, that if we want to have a whole event, it's not enough to just remove the points. We have to balance it by moving zeros from the outer part somehow to the boundary. This sort of was found some prediction of Misha-Sonin, and this is the picture that we get. So there's this circle again is just the zeros, all of the zeros that were moved from the disk. Here we condition on no zeros inside the disk, so we had to move them to the boundary, and we had to bring some zeros as compensation from the outside, and this leads to the accumulation of many zeros around the boundary of the disk. As you can see, there are some spurious zeros running around here, which are still in the forbidden region, but in the limit, the density of the zeros in this region vanishes. We also did some other stuff about deficiency and overcrowding, and we found, as I showed you before, what happens in those cases. And also before us, Nazarov, Sodin, and Warburg, they proved that the JLM predictions, which were from Coulomb gases, also hold for this event. And now, in the non-circular case, we don't have a determinantal structure. We don't have radial symmetry of the Taylor series, so it doesn't help us. And there is no connection to some familiar objects for potential theory, so this poses a major problem. And with this recent work with Aron, we actually found which shapes of the hole will lead to a round forbidden region. We found out that there's something non-trivial happens here. I will show you a picture in a bit. And we can also describe what kind of shape the forbidden region will take, this region where there are no zeros in the limit outside of the hole, which we call a forbidden region. What kind of shapes? It turned out that there is a great sort of rigidity in the shape of the forbidden region. It cannot take just an arbitrary shape. And we had to develop some new methods, so this I will defer to Aron. So I will just mention the one theorem, and then we'll show a picture, and we'll finish with this. So we have some kind of a conformal rigid structure that hits there. So a domain, simply connected domain, is disk-like. I will normalize it to have center 0 and radius 1. If we consider a normalized Riemann map that maps the domain to the disk, takes 0 to 0, and the derivative at 0 is 1. And it satisfies some inequality. That means that the domain cannot be too far away in some conformal sense from a disk. And what we said that if this condition holds, then the forbidden region is a disk, and this is an if and only if condition under some rather weak regularity condition. And in this case, we can also say that the measure of this singular component, the thing that lives on the boundary, is harmonic measure as seen from the point 0. So I will just show it a final picture, and we'll finish here. So one can check that, let's say, equilateral triangles are not disk-like, so they don't satisfy this property, but squares are disk-like. And this means that for a square, the forbidden region will look like a disk. And so that we still have to, if we want to condition on having no points inside a square, we have to move points from a disk around it to the square. For the Geneva Ensemble, as you can see, this is looks the same. So the process outside doesn't see any effect. We just have the points on the boundary, while for the zeros, we do have the points on the boundary, but we also have to balance it by bringing points from the outside. And also, if you'll notice, the measure on the boundary is different from these two processes. But I think I will stop here So if you have questions about it, I can provide more details. So thank you for listening.
Okay. So thank you, Alon. Any questions, comments?
Couple of questions, Alon. One is that what you said about, again, I want to just confirm that in the middle, when I said the scaling for the Gaussian zeros also in the large deviations is the same thing.
Yes, if you ask about the probability of these events, it also decays like r to e to the minus some constant times r to the fourth.
Okay.
Mm-hmm. Yeah.
But the difference comes in the constant.
All of these JLM predictions for moderate deviations and large deviations, with study events where the distance from the expected number of points is, let's say, some power of the expectation. So not the expectation to the power 1, but the expectation to some other power. They also match.
Okay.
So do you want to say what is the JLM prediction? I mean, you mentioned it many times, but
okay, maybe let's see if I have some space here. So let's consider just the disk. So let's write n of r, that this is the number of points in disk, so that the expected number is r squared. And now the question is, you can do more precise things, but let's the basic question, we compare the number of points to the expected value, and we ask what is the probability that there is some discrepancy. So this will be minus some constants that I'm going to ignore. So let's write it like this. So minus r to some function phi that depends on alpha, and the JLM prediction give a prediction for this function phi. The interesting thing is it's a piecewise function, so there is one thing that happens. I will not draw exactly how the function looks like, but approximately it's this. So let's see, with my scaling, I think I should put here different alpha. So I want to do the scaling that 1/2 is the central limit theorem. So central limit theorem corresponds to fluctuations of size square root of the variance, which is square root of r. So maybe I will just put here, instead of this is just scaling, I will put r to the alpha. So here there is a CLT, and then there is a regime where you have a large deviation, a moderate deviation. So the tail behaves like a sort of like a Gaussian random variable. For this relatively small fluctuations, it still behaves sort of like a Gaussian random variable. And then there is a transition. Maybe there is a transition, and then there is another transition. So there is a overcrowding, extreme overcrowding regime, which behaves in one way. There is a large deviations regime, which behaves in a different way. And then there is a moderate deviation regime for the smallest fluctuation, which behaves like a Gaussian. And they have a physical explanation of why this is true for this Coulomb gases, where the Ginibre ensemble is one example in a specific temperature, we can think of it, and they have explanation what happens for all temperatures. It's not very, it doesn't really depend strongly on the temperature. And Nazarov, Sony, and Wahlberg proved that exactly this kind of picture you see also for the zeros. This is still a bit mysterious to me, why there is sort of this universal behavior. For some other model, for example, in a hyperbolic plane, it's not clear that, for example, that you have the same behavior. It might be different. But for the plane, it's somehow a natural behavior for this type of processes. Of course, you can cook up processes with other with different behavior, but for some kind of processes which are Ginibre-like or zeros-like, you see this behavior occurring. So I hope this added something, Manju.
Yes, yeah. No, that was very good. Yeah. I have one small question about the disk-like that you had regions which were disk-like. So I haven't. I mean, so is this some? I mean, this is not your definition, right? It existed before. Or what is this disk-like?
The disk-like?
Huh.
Not that I'm aware of. It is somehow natural. It's a bit obscure, but this is if you look at the functional carefully, it will be more. It will make a bit more sense. I need more time to explain the why. But maybe Aron will have the time in his talk. But the interesting thing here is that so of course this is just a normalized situation. In general, you can have a center Z naught, let's say, and a radius R. And then if you have this center and radius, they are unique. Okay, so it's kind of it is a real sort of conformal property. And the nice thing is sort of characterize exactly the situation in which the forbidden region is the disk. So somehow there is like we see in this picture. I mean, it's not true that the square is geometrically close to the disk, but I guess in the sense of this process it is. And the interesting thing is that this thing around is sort of very conformally rigid with respect to the shape of the hole. So it stays as the same, and it's true also for that we can say a lot of things about. So there is a strong restriction on the shape of this forbidden region outside, even compared to the Ginibre, where basically there is absolutely no restriction. Any shape that you will do it, the hole will just fit. Like this boundary will just fit, and you can tell exactly what is this boundary. I can say a few more things if you're interested.
I was more like asking. I mean, I guess Aron will talk about this whole problem, but there in the condition, should I really think of Z close to the boundary, or I mean, there is a condition for all Z in G. What is the crucial point? Is it Z close to the boundary that one needs to worry about?
I'm not sure it's enough, actually. I now I understand your question. I didn't think about it carefully enough to if like you can reduce it to some easier to check conditions. That's a good question. Aron, do you have any insight, immediate insight into this? So it could.
No immediate insight. I know that the cases I checked where it breaks down also on the boundary.
Okay, so this gives a partial answer, I guess. Okay. But I don't know if it's true that it's enough to check it on the boundary. That's a good question.
Okay. Any other questions?
I had one regarding the statement of the theorem with Gauche. I mean, empirical distribution, how does one interpret here? Because the process is infinite, right? So you let the limit n go to infinity and then R suitably.
So for the infinite process, you can consider test functions, which are, let's say, I don't know, continuous test functions with compact support. And then basically you integrate them against the infinite zero process. This is fine because they have compact support, so you get a perfectly fine random variables, and these have to converge for each compact test function that you choose. So this is a more precise probabilistic statement.
Okay, thanks.
Okay. And these actually, yeah, it's a good question. This converge. You can say more precise things, but let's say that this converge in distribution.
Okay.
To the thing to the thing which corresponds to integration with. So you take a test function, I don't know, phi with and then you integrate phi against the zeros of the process. Let's write it like this. And this random variable converges to the integral of phi against this measure. Okay.
Okay.
You can do more precise things, even control how many points are in this forbidden region, because there are some points there, and do all kinds of things. But I won't get into the details.
Okay. Thank you.
Okay. Okay, so maybe we can take a break now. We are already at 3:26, so maybe we'll take a 10-minute break, and or let's resume at 3:35. Maybe is that okay, Yogesh? So yeah, let's take a 8-minute break. Sorry, I clicked something by mistake. Okay. Okay, so we will now start on the second lecture by Aron Wennman, who is also from Tel-Aviv University. Before that, he was a PhD student at KTH with Hakan Hedelman, and now he is a postdoc at Tel Aviv. And he will tell us more about this surprising behavior of the quadrature domains, or the last result that Alon referred to, when conditioned on a large hole in random zeros. Aron, please.
Thank you so much. Thank you so much for the invitation and the opportunity to give this talk. So I will continue to speak about the joint work with Alon. Here's an overview of the talk. I'm not completely sure I will have time to do both 4 and 5, but we will see where we are at. So I will begin with a quick recap of this statistical mechanics interpretation of random zeros. Compare a bit more in depth, maybe with the Geneva Ensemble. Move on to what we prove for a general, when the whole is a general Jordan domain and not this disk-like thing. And in the end, hopefully say some words about the tools we use and what we develop related to potential theory in PD. So we begin with the main player, which is the Gaussian entire function. And here I already look at the rescaled variant. So I have a scaling parameter, capital R. Alon used little r, but so it's just this random Taylor series where xin are IID Gaussians. And with the same normalization as before. So this is a random entire function. It's zeros. It's an invariant process in the plane with intensity with respect to the Lebesgue measure, which is pi r squared. And we prefer to so with this scaling, when we consider the whole event, the whole will be fixed, and r will the intensity r squared will tend to infinity instead. And we approximate this by its Taylor polynomial of degree n, just truncate this series at z to the n. And the reason why we do this is because then we have access to this nice expression for the joint density of zeros. And we can also normalize the corresponding empirical measure to be a probability measure, which also is technically helpful. So the parameters I should dwell on a little bit. So we will choose n to be like some parameter alpha times r squared. Here, so if we choose this, then this polynomial will be a very good approximation of the entire function on a disk of radius square root of alpha. So if we want globally to have a good approximation, this alpha should also tend to infinity with R, but it will tend to infinity very slowly. So you can just think of it as almost like a fixed, very large parameter, but always arbitrarily large. So this will mean that I will never have any issues where somehow the behavior near the boundary of the region where the zeros of this Taylor polynomial lives, this will never interact with the whole. So I might be a bit sloppy between switching between this function fr and the polynomials, because some of these boundary effects will never come into play for us. So this density here for the random polynomials, we have this van der Monde term, which is the product of all the pairwise distances between the zeros. And then we have this confining effect obtained by dividing by the L2 norm of the corresponding monic polynomial, QZ, where we put zeros at the Z1 up to Zn. So if this norm is actually minimized if all the zeros fall into the origin. And if all the zeros try to spread out, then the norm of this polynomial will be large, so the value of the density will be small. So this is the way in which it confines. So again, we compare with the Ginibre density, which is you have some normalizing constant, you have the van der Monde determinant, but a much easier confinement. Easier to work with because it's linear in the empirical measure. So we use some notation from potential theories. So for a measure mu, which we will always have compactly supported and with finite logarithmic energy, we consider the potential, which is just obtained by convolving with the logarithmic kernel. So this has the property that if you take the Laplacian of your potential, you get back your measure up to a positive constant. The logarithmic energy is just obtained by so you integrate minus u mu against mu again, or if you want the double integral of the inverse logarithmic kernel. So this van der Monde determinant is the exponential of an energy, but the discrete energy obtained by removing all the diagonal terms. Otherwise, you would have like the self-interaction for an atomic measure is divergent. But for good measures in the limit, we will be able to replace this discrete. The effect of the singularity will play a very little role. I will use throughout mu sub boldface z will be the empirical measure, which I normalize appropriately. So here, I will not focus on this too much at the moment, but if you look at the formula for the energy, sigma mu, it's the negative of the integral u mu d mu. So if you play around a bit with the Fubini, you see that if the potential grows, so if you have two measures, u mu, and consider the potentials u mu and u nu, and if the potential of one measure is larger than the potential of the other, then the inverse relationship holds for their energies. So when the potential grows, the energy of the measure decreases. So, and we will want to minimize energies. So typically this corresponds to wanting to construct as large potentials as possible. This is a heuristic which is good to have in mind. Okay, so this exact density has been known, has been around for a long time, but as Alon mentioned, what really allows us to work with it is a simplification at the level of bulk statistics that Zaitouni and Selic did. So very, very roughly, the approximation is the following. So we work at the scale of the logarithm of the density, and if we normalize appropriately by 1 over n squared and look at the confining term, then you can rewrite it roughly as 1 over n times the logarithm of this thing here. And the reason is that the potential of this empirical measure mu z, so here the z came in the wrong place, but the exponential of u mu z is just this polynomial qz, the modulus. So the L2 norm can be rewritten in this way. And the main contribution to such an integral will come from the place where this the term appearing here in the exponential, where this attains its maximal value. This will give almost all the contribution from this integral. And if you simplify and look what the main contribution is, then you realize, this is actually this supremum that appeared in the previous talk. So this whole term is roughly going to be 2 times B alpha mu, where B alpha mu is this functional. So you take your potential, U mu of W, and you subtract what is the potential of the uniform measure, W modulus W squared over 2 alpha. So alpha is this constant relating the number of points to the scaling. And you look for the maximal upwards deviation. So you look where this deviates upwards from this most. So the supremum over the entire complex plane. So if mu now was a measure supported, say, uniform measure on a huge circle, then the supremum would be attained at the origin and it would be large. So this prevents from the points from running away, or the mass from spreading out too much. So this is the confinement term that we get. And this van der Monde term gives, as usual, an energy term. So in the end, we obtain this. We can think of the density as what's known as a Gibbs type measure. So it's e to the minus n squared times this functional, and the functional is the energy plus this confinement. So if we are interested in the whole event, so now we consider the whole event for the zeros of the polynomials for simplicity. So we look at the event that Pnr of z is non-zero for all z in some domain G. And here n is alpha r squared with alpha large. And as Alon explained, in order to understand this, what we really need to understand is the minimization of this functional I alpha of mu. And we minimize overall probability measures mu which give no mass to the whole. So this is the actual problem that we are considering from now. There's a lot of work to be done to actually connect it to the random zeros, but for the purpose of this talk, this is the problem that we want to consider. So I will begin with a simple reformulation of this problem. So we have this B alpha of mu. So the first thing that we do is we prove the following lemma. So we show that this part of the functional can actually be moved from the functional into like an additional constraint. What I really want to say is the following. Suppose you know that B alpha of the extremal measure, the measure we are looking for, is some given value C0. Then there's no loss in restricting the minimization of measures which have this property. So you can just minimize your potential I alpha over the class of all measures which satisfies this inequality with equality somewhere. This is to say that B alpha of the measure takes the correct value. But then I alpha, this is just a given constant plus the energy. So minimizing it is equivalent to just minimizing the energy. So the content of this lemma is slightly more. We're not saying that we're not saying that this supremum is attained anywhere. We're saying that it is, in fact, it's attained anywhere for large z. We're saying that this constant C0 is actually independent of the domain G. And the reason for why this holds is that when alpha is really large, far away from the hole, the conditioning is not really felt. So in fact, the extremal measure here, when we under the constraint mu G is 0, will be a compact perturbation at the level of the potential, compactly supported perturbation of the extremal potential when the hole is not there at all. This is non-trivial to see, but this is somehow this is the spirit of how we prove this. So really, this is a simple trick that you can sometimes play with when you're minimizing a functional. and somehow you move some part of the functional into a constraint. So now we're minimizing something which is very classical in analysis. Minimizing energies is something that people do a lot. And we minimize overall measures whose potential satisfies some inequality. And of course, we have to still insist on this condition, mu g is 0. Okay, so this is the problem that will stay with us. Before I move on, let me say a few words about the Geneva Ensemble. So in the Geneva Ensemble, if we still want to have this kind of scaling, so we consider larger matrices of size n by n, and we rescale everything by r. So we also have some parameter alpha here. This parameter appears in the energy functional for the Geneva Ensemble in this way. If we don't condition on anything, then the minimizer is just a uniform measure on the disk of radius square root of alpha, as for the zeros. So this problem was studied, as Alon mentioned, by Adhikari and Reddy, by Armstrong, Serfati, and Saitoni, and some other people. And here we can use some fact from potential theory. So this kind of energy functional is known as a weighted logarithmic potential, or a logarithmic potential in an external field. And it's a classical topic. There's a book by Safan Totik which treats this in very large detail. And in fact, minimizing this under the constraint that mu g equals 0 is the same as considering the unconstrained minimization problem for a related functional obtained by putting the external field to be plus infinity inside G. And the external field will be unchanged on outside the hole. So here we don't have to insist that mu g will be equal to 0, but it will happen automatically. And if now the domain G lies inside this disk square root of alpha, like a disk of radius square root of alpha around the origin, this is important. If this does not hold, then there's no way to solve this exactly. But if this holds, then you can write down the exact solution. So what you do is you take the potential of a uniform measure, and you keep it outside your hole, but inside the hole you replace the potential by the harmonic extension, or the Poisson integral of u mu to the domain. So here I try to show this. So you have this parabola, which is the potential of uniform measure, and you look at the whole problem for a square. So the potential of the constraint solution is just inside the square is just the Poisson extension of the boundary values given by mu 0. And the effect of this on the actual measure is that the optimal measure is mu 0 on the square hole event, say, is obtained by outside the hole you keep what you had, but inside the hole you take so omega g here is harmonic measure seen from the point W. So you sample W from your unconstrained equilibrium measure, and then you average the hitting density on the boundary of this point. So you can think of, so each particle that was inside the hole independently will do a Brownian motion until it hits. So this will be the average of Brownian motion hitting probabilities over all particle locations that you would see without the hole constraint. Let me move on. Okay, so moving on to our actual findings. First, let me do some very brief recap of some potential theory. So if U is a subharmonic function, if U is C2 smooth, then you can just think of it as its Laplacian is non-negative. And you can consider less smooth subharmonic functions, and then you think of the distributional Laplacian should be a non-negative measure. So if U is subharmonic on a disk D around a point Z0 in the plane, then there's a classical result or almost like an equivalent definition saying that z0, the value at the center of the disk, should be bounded above by its integral mean, normalized by the area of the disk. This is known as the sub-mean value property. So if you have dj a disjoint collection of disks, then if U is subharmonic on their union, then just rewriting this gives that the integral over the union of these disks is bounded below by the sum of point evaluations of U at the centers of Cj, and you have to multiply by the measures of the disks. So this is just a triviality here, but I want to use it to motivate the next definition, which is that of quadrature domains. So we have some measure, some finitely supported atomic measure nu. So here we have some positive numbers rho j and some points lambda j. They lie in some domain omega. And we say that omega is a quadrature domain with respect to this measure. If for all bounded subharmonic functions u, the same kind of sub-mean value property holds. So the integral of a subharmonic function is bounded below by such a point evaluation. So this, it might be good to stop and think what happens if u is harmonic. Then actually both u and minus u are subharmonic. So then you can convince yourself that this has to hold with equality. So for harmonic functions, you get what's known as a quadrature rule. You can integrate a function over the domain by just a finite number of point evaluations. So for each atomic measure nu, there is a unique quadrature domain omega nu. And you can think of it as somehow as a generalization of a union of disks around the lambda j of radius square root of rho j. If in fact the disks are disjoint, then the unique quadrature domain is just a union of disks. But if they overlap, then this is somehow a way to smear out the overlap into a domain to keep this sub-mean value property. And this is another name for this object. It's the smash sum of these disks. So here I just kept the definition, and I have some pictures. So the first row is well, just disjoint union of disks. But in the second row we have here overlap. So we have a bunch of overlapping disks, and we have drawn the associated unique quadrature domain omega nu is drawn. This is credit to this picture goes to Yasin Amer and co-authors. So you see here, if you increase the radius of the involved disks, then the quadrature domain omega grows. Okay. So Alon said that he explained our results saying that whenever our domain G is a nice simply connected domain which meets this disk-likeness condition, then the conditional limiting zero distribution on the whole event will have a circular forbidden region. So there's this region around the hole where the asymptotic zero distribution, zero density vanishes. So first thing that, first result, which is maybe not so surprising, is that if you replace the disk-like hole by any reasonable hole, then there is still a forbidden region. And what we ask is what is the shape of this thing? Let's see. And this is our result. So assume that G is a Jordan domain, so its boundary is a simple closed curve. So assume that this is C2 smooth. Then our result is that there exists a finitely supported measure. So there are finitely many points lambda inside the whole G, and associated positive weights rho lambda, such that the forbidden region is actually one of these quadrature domains. So we can say slightly more. We can say that the limiting measure that describes the zero distribution, it actually takes the form, so uniform measure on the plane with this quadrature domain removed, And then we have a boundary density, which is going to be a finite linear combination of harmonic measures seen from this point lambda. So the disk-like condition corresponds to, so the disk-like holes correspond to having just one harmonic measure here, and the 1-point quadrature domain, which is just one disk. But when this is violated, it's not that the forbidden region can take any shape. It still has to remain with this, within this somehow family, which is parameterized by these finitely supported measures. And these quadrature domains, I will not go into depth about it, but they are fairly special. So there's a polynomial in variables x and y that describes the bound. There's a polynomial equation that describes the boundary. So the boundary is an real algebraic curve.
One question: is there something more? I mean, are these more explicit? The rho lambdas and the lambda, is the structure more explicit? Or
no, so this is we had this somehow perfect condition in terms of the conformal map of when you have only one of these points lambda. But when it becomes more complicated, in principle, you could write conditions for when it is a 2-point quadrature domain and so on, but they very fast they become intractable. Basically, since you cannot really compute the potential, you cannot compute the potential of a quadrature domain unless it's the disk or some very specific instances. But to write concrete geometric conditions for exactly which omega nu corresponds to a given g, this still remains open.
Okay, thank you.
And this is, yeah, I put this. So the geometric connection between g and omega, this is not clear at the moment. Okay, so I will move on to describe some of the tools that go into studying this minimization problem. The first thing we want to do is replace the logarithmic energy, which is slightly mysterious, with something which is more easy to work with from the point of view of analysis. And this is the Dirichlet energy. So the Dirichlet energy is defined for functions. Well, you can begin by smooth functions, but in the end, in the Sobolev space H1. So the H1 is what's known also as W12. So you have one derivative of the gradient, and the function should lie in L2 on some domain omega. And the Dirichlet energy, which we denote by script d of u, is just the integral of its gradient modulus squared over the domain. So if you know slightly more about the potential, suppose you know that u mu and the gradient of u mu, they are some fixed functions on the boundary. For us, they will just be, we know that far away from the hole, the potential is radial. So we will know the potential of our measures far away. And if this is the case, then you can do the following trick. So sigma of mu, this is just by definition the integral, this first integral here. And the measure mu by the defining property of the potential is just u mu times Laplacian of u mu up to a constant. So then you can just apply Green's formula and see that, aha, this sigma of mu is just the Dirichlet energy plus a boundary term. So if you a priori know what this boundary term is, then you can just focus on minimizing the Dirichlet energy of the potential instead. So we can freely move between minimizing sigma and minimizing the Dirichlet energy if we just keep track of the potential on the boundary of some, say, large disk. So minimizing Dirichlet energies, as I said, is very classical in analysis. The most classical instance is if you minimize the Dirichlet energy over all H1 functions which have a given value on the boundary of some domain. So then you obtain just the classical Poisson extension, the unique harmonic function inside the domain with the given boundary values. This is not so difficult to believe, because if you let U0 be the energy minimal solution, then what you know? Well, you know that whenever you have some competing function, for instance, a function which we can cook by u epsilon to be some compactly supported smooth perturbation. So you take some test function phi and you add epsilon phi. Then you know that the energy of u0 must be smaller than the energy of u epsilon. But you can just write to the first the first variation of this the first variation of this energy is just going to be the 2 times epsilon times the inner product of gradient of u0 with the gradient of phi integrated over the domain. And then you have some higher order terms. So if the energy of u epsilon is supposed not to be smaller than the energy of u0, then this has to be 0, because we can consider both positive and negative epsilons. So this kind of integral of u or u0 here, this inner product has to be 0. And this is just to say, this is just by definition almost, that the Laplacian of u is 0 in the sense of distributions. And we began with a function which had the correct boundary value. So this has to be the Poisson extension if f is a reasonable function and omega is a reasonable domain. So this is quite far from our problem because we had a lot of extra conditions. But we will try to add one at a time until we reach something which is more similar to what we're actually dealing with. So first, let's add this condition that the potential is not supposed to exceed the given function. So we have some function psi here general, but you can just think of it as absolute value z squared times some constant. So you have this and you have some boundary datum f on some domain D, and you want to minimize the Dirichlet energy under these conditions. So u equals f on the boundary of the domain, and u does not exceed psi. So the difference here is there will be a unique minimizer if the data is regular enough. The only difference is that you cannot completely repeat this perturbation trick, because there's this obstacle that prevents you from perturbing. So this is known as the obstacle problem, and psi is this obstacle or global obstacle. So there will be some region likely where u is strictly smaller than psi, and in this region you can do this exactly the same trick. So in this region, by the same argument, the solution will be harmonic. And then on the other set, well, you know what it is because you know that it equals psi. And in compact notation, you can write it like this. So either u equals to psi, and this term is 0, or u is strictly smaller than psi, but then u is harmonic, so Laplacian of u is 0. So this is a compact equation for the conditions of minimality. And in fact, you can say slightly more. You can also exclude that there would be some mass of the Laplacian of the solution exactly on the boundary of the sets where u is equal to psi. So you can say that, in fact, Laplacian of u in the sense of distributions will just be Laplacian of psi times the indicator function of some nice set. So this set is known as the coincidence set, u equals to psi. And this means that u is going to be quite regular. So u will not be C2 smooth because there might be a jump in the Laplacian, but its gradient is going to be continuous, even Lipschitz continuous. So here I've drawn a picture. So here I've actually drawn minus the solution of the obstacle problem because it's much easier to see. So here we have Dirichlet conditions on a square. The solution is 0 here on the square. And then the obstacle is just absolute value z squared. And the solution of the obstacle problem is going to be harmonic in this blue region. And then on this red region is where it makes contact with the obstacle. And the transition between the two is going to be it's a smooth thing. The gradient of the solution doesn't jump. So I should say I plotted this. We did the numerics in a program called Phoenix, which uses the finite element method, and we plot it using software called ParaView, which I like a lot, both of them. Okay, so the last level of complication I want to add to this minimization problems is what's known, considering what's known as a mixed obstacle problem, or mixed dimensional. So there we have, in addition to a smooth function psi and some boundary values, we will have some curve. Think of it as actually as the boundary of our domain G, where we condition on having no zeros. And on this curve there will be some function G, and we add the condition that U does not exceed this function G on the curve. So this is, and then we consider again the Dirichlet energy minimizer among all functions lying below psi, say which are equal to psi here on the boundary, and which lie below G on the curve. So it's very similar, just that there would be some, of course, where you don't touch any of the obstacles, the solution will be harmonic. But you will get a jump in the normal derivative right at this thin obstacle, the obstacle along the curve gamma. And if you can see from Green's formula that this jump in the normal derivative will actually be the distributional Laplacian of your solution. Now, what's the main point here? The main point is that if this thin constraint, which is illustrated by the red dots in my picture, if this is far enough below the global constraint, U bounded above by psi, then automatically inside this curve, the energy minimizer will not touch this dashed line with the global obstacle psi. So you can just imagine, if you pull these red dots down far enough, then you will not touch the global obstacle. And then automatically, from properties of the solution, you will be harmonic inside. And remember, we want to consider measures which don't give any mass to the domain G. So if gamma encloses G, then one way to cook measures which have no mass inside is to choose this boundary obstacle small enough. And in fact, you can find the solution in this way. So this is our, in a sense, our real starting point for the actual analysis. This is the following lemma. So I call it an implicit obstacle problem, and the formulation is as follows. So I claim that there exists some function G which lies in the appropriate Sobolev space on the boundary. You can just think of it as slightly better than an L2 function. There exists some G on the boundary such that if I consider the minimizer of the Dirichlet energy among all functions which are bounded above everywhere by absolute value z squared over 2, on the boundary of some disk, it should be equal to the z squared over 2, and on the curve G, on the curve boundary of G, we require that U is bounded above by G, lowercase. Then the Laplacian of this function is my solution to the minimization of the functional I alpha among all measures which give no mass to the whole. Nobody has told us what this function G is, but I just claim that there exists some function G with these properties. And this regularity is just enough that the problem on the previous page makes sense. Now this is far from the quadrature domain theorem, but in fact already this and just standard properties of obstacle problems implies that there is some forbidden region. It implies that where you have density outside the hole, the density will be 1. And there will be some singular distribution of mass on the boundary of the hole. So you get like the general structure, but you don't get the shape of the forbidden region, and you don't get what the actual boundary density is. But this is the content of like to go from here to the actual main theorem is what we do in the paper. I have a few minutes left, so let me just go through a scale of examples. So here we have 2 points at plus minus 1, and then each of the points we put symmetric positive masses here and consider the corresponding 2-point quadrature domains. Then we get what's known as the Neumann ovals. These are family of domains which grow with the masses, and their boundaries are given by a polynomial equation of order 4. So these are just examples of quadrature domains. Now consider here condition on having no zeros inside two unit disks which are far apart. Then by a small modification of the result by Alon and Subru-Ghosh, each of them will have a forbidden region, which is also a circle. So the inner circle here is our conditioning, and then you have a forbidden region, which is the larger white circle here. And they don't, if they are far enough apart that the forbidden regions don't touch, then you can consider this problem somehow separates. Now we will move these two centers closer and see what happens. So when these centers are moved slightly closer so that the forbidden regions just touch, you get one of these Neumann ovals, the 2-point quadrature domain. The center of the quadrature domain will not match with the center of the disk. It will be a slight perturbation, but you can compute what it is. And then we can continue the evolution. We move the disks closer and it stays a 2-point quadrature domain, just with different parameters.
Eventually, say that the gray thing is just like the uniform, like the sort of.
Yes. Yeah. So you have the gray thing outside is just uniform mass, and there will be some distribution of mass on the black things as well, but I didn't indicate the density of this. But it's going to be some harmonic measure all the time. Okay, so at some point the inner disks touch as well, and then we just, for aesthetic reasons, choose to evolve this as a quadrature domain as well. But this is our choice, and we could likely get the same result with other evolutions. But the outer boundary stays a quadrature domain, and after a while, the inner thing is circular enough that in this specific sense it's disk-like. And then the forbidden region would become a perfect circle. Here we have tried to numerically find exactly the threshold for when this happens. And if you continue the evolution of the inner thing into a more and more circular thing, the outer region stays exactly the same after scaling. I think this is all I wanted to say. I'm happy to answer any questions you might have.
Okay, thank you. Any questions?
I have one.
Yes.
So I have a basic question on the obstacle problem. I know your motivation for D was like a disk-like object, but does it hold for any general domain D, that lemma that you showed?
Let's see, what lemma? This thing?
Yeah.
Yes. So this lemma holds. This holds whenever, I think, for any Lipschitz domain G.
D. What about D?
So D is just a large disk. So here and I mean D is just for here. Yeah, it's just some actually the disk of radius square root of alpha.
I see. Oh, that's what the dependence on D is. Okay.
Yeah, but yeah, you could actually take anything which is much larger than the hole itself, and then closes the hole.
And somehow is this accurate interpret that somehow the G doesn't depend on how D looks like? Is that correct?
So let's just okay. So the data here is actually script G. So this is the domain where we condition on having no zeros.
Very good, yeah.
And D, this doesn't care at all about.
Oh, that's right. Very good.
It's just something which isolates us from infinity.
The G is just dependent on D. Thank you.
Like on the same point, is it because also like you are going to do this sort of integration against compact test functions? D is something that's like the support of the test function or so. In this convergence business of the conditional distribution of the whole, you are in some sense restricted to a large domain containing G. Is that the point of D?
Yes, yes. So the point is, basically the point is here. At some point we want to move from the logarithmic entity to the Dirichlet entity. And the Dirichlet entity works well when you have compactly supported things. So what we do is we first prove this lemma, which says that okay, so for any reason, our parameter alpha goes to infinity, and when alpha is large enough, then if we move far away from the whole, then we really don't see any effect of G at all. So if alpha is huge and you look at the scale of this disk of radius square root of alpha, then the conditioning is just some tiny thing happening in the middle, and far away you don't see it. And you use this somehow to compactify things.
Okay.
The key action is what happens close to the hole, and what is this function little g.
Also, another question: when you say forbidden regions, you also mean by conditioning on fewer points also in the domain, not just no points. In the examples you said you put no points inside the domain, but this forbidden region also include things with fewer points in the domain.
So what we prove and what we actually work on in the paper is only the whole event.
Okay, okay.
But as Alon showed for the circular case, they know what happens also. Sorry, I saw some question in the chat. They know what happens also for the undercrowding and overcrowding problems. Some of our techniques generalize to say something about these deficiency and overcrowding problems. Most likely, it's not done anywhere. But some techniques should generalize, but we won't get any precise results like the forbidden region will be a quadrature domain or things like this.
Okay.
Yeah, there is one question in the chat about the. Yeah, so you see it about.
Let me just find it. I can find it when I'm in full screen. Can you just read it?
Yeah. So the question is from BV Ram, and he says the results are for domains with smooth boundaries, but how do you conclude that square is disk-like? In this case, it's a piecewise smooth boundary.
Yeah, so actually our results apply to piecewise C2 smooth boundaries. We will not have exactly the same statement, which is why I didn't include it. But let me go back to the quadrature domain theorem. Here, if you insist only on having a piecewise smooth boundary, then this measure nu will not necessarily be a finitely supported measure, but it will be a measure supported on a union of analytic curves, and these analytic curves can have to connect singular boundary points. And this is enough to get like the one condition for to get one direction for this disk likeness theorem, and the other direction doesn't care about smoothness at all. If you have a conformal map which satisfies this property, then to say that this is a solution to the extremal problem is not as sensitive to regularity concerns.
Oh, in that case, by looking at the measure mu, you can decipher the number of singular points on the boundary?
No, you can bound it. You can say that if nu goes all the way out to the boundary, then you have a singular point there. But you cannot say that. In fact, the measure for the square will just be a point measure in the origin. So it allows for this thing to happen, but it will not always happen. In fact, we don't know of a single example where the measure actually goes all the way out to the boundary.
Thank you. Thank you.
So on the same point, I have this, just to clarify, in case of square, you are saying that this condition measure is just the harmonic measure from the center. Is that correct?
Yes.
Not the singular
Yes.
point. Whereas in the case of Ginibre, it is integration of several harmonic measures. Is that
Exactly.
complex combination of with respect to the equilibrium measure or something?
Mm-hmm. Exactly.
Right.
So there are some different, different probabilistic interpretations. I don't know what the interpretation is of our harmonic measure from a center point. Somehow all the points rush to the center point and then distribute from there. If you just look at the obvious, like a naive interpretation.